Please subscribe, like, and share. Today we will talk about the intake side of the valve spring. We will show the forces acting on the valve, as I showed earlier on the previous video, the way exhaust velocity and combustion pressure tries to keep the exhaust valve closed, thereby assisting the exhaust valve spring. That's why I tried to give some kind of indication why you can safely remove some pressure off your exhaust valve spring and without any adverse or negative effects that might be detrimental to your engine. Today I will show right on this flow bench what the forces are among the intake flow, what the forces are acting on that is contrary and fighting the intake valve spring for control of the valve. But before we continue on, I just like to do these things because I just don't want to make a general statement without showing, just like I did previously, what the forces are acting on the exhaust valve, thereby, like I said, benefiting the exhaust valve spring. Today we will do the same thing here on the intake. The forces acting on the valve working against the intake valve spring. And here it is. Here we are, we're looking at that valve. And watch this when I turn it on. Amazing dynamic, isn't it? You can see how that valve is trying to be pushed open by the velocity of the incoming air through the intake port. And I don't even have a radius plate installed. If it's got a radius plate in there and it's a real running engine, that draw trying to open the valve would be a lot more significant. Remember, this is just a small flow bench. As you can see there, I'm trying to hold the stem of the valve and I'm holding it, and as soon as I turn on the flow bench, it just draws it in by virtue of the intake draw, or like what a lot of the guys are doing, the suction. I have to use that. Anyway, I'm trying to get used to this thing because this is automotive. Thereby acting on the valve, and come to think of it, there's still, this is just a flow bench. There's not much force as opposed to a real running engine, which has a lot more draw power acting on that valve. And I will explain on this whiteboard how that is. When your coils starts vibrating right about here where the coil would usually sit, or above here past the screen, it will start to give a lot of vibration, oscillations, all sorts of motion, commotion, monkey motion into the valve stem, unsitting the valve sealing capability. Because remember, when the piston, when that valve is wide open, all the air and fuel is rushing in there. Okay? When it's rushing in, suddenly you shut it off. All these airflow, all these come in here. Boy, it's hard to draw when you're looking through a camera. Excuse me, guys. All right, so all these things come in, all the column, and when they hit this close intake valve, guess what they do? Go back up, go back up, go back up, And guess what? Incoming waves also hit that. All right? So port is trying to recover pressure. And when it does, it slams in here. So when you have the force of the incoming air column coming in and putting pressure on the valve head to try to open it from all the other pulses or intake pulses coming in or preceding waves, and then the oscillation of the coil spring on top. So basically the whole valve will start to vibrate, and that's the time you see the RPM dip or the horsepower dip on the dyno. When you look at the dyno reading, let's say at 6,000 to 7,000 RPM, it's going up quick, it's going up, and then suddenly there's a dip, and then it starts going up again. That dip right there is the oscillation of the valve unsitting because of all the harmonics, all sorts of stuff going on, coil oscillation, natural frequency, everything there creates instability. Okay, this is a continuation of our previous video. What we have here is a standard valve spring that everybody's been using all these years. And I do not have a sample of a beehive. I figured we'll jump past the beehive and go straight to this new style conical spring. The beehive is better than the standard valve spring on the left, but I figured we will just jump straight across to a conical, which is vastly superior to any kind of beehive spring. So here we go. Let's set it aside. The straight cut or straight valve springs, like we've used for many, many years, the standard springs have what we call one natural frequency, meaning one natural frequency for one coil. Since they're all the same dimension, it starts here and progressively does the same on all of them. Basically, this acts like a guitar string. Once they harmonize from the first coil, the middle coil, or the bottom coil, they'll go all the way across because they are like spring winding. It's all the same in there. Therefore, you got to make sure that we know this compared to this guy right here, which is the conical. Now, all the valve train movement from the rocker arms to the push rods to the valve springs, of course, all these things from the valve lifters, all these things that go up and down in a repeated motion at ever-increasing frequency or RPMs. And all these valve train movement and vibration contributes to spring instability. This one starts to wobble around, or like what I said earlier, they do the hula dance. That is really bad stuff. Yep, when resonance sets up, they do the hula dance and crashes to each other. When these things are doing the hula, for a lack of a better term, they start to collide to each other. And remember, the stress is right here in the middle. Most of the work is happening between the upper and lower spring. And basically when they start bouncing around like that, they crash it to each other, and then that's when they get damaged. Also remember, when these valve springs start to resonate like a guitar string, they will start to really vibrate severely, transferring all that harmonics straight to the valve. Even the rocker arms could also have harmonic tendencies, but this is really, really very bad because it's directly connected to the valve stem. And when they do that, it starts to gyrate the intake valve or the exhaust valve, contributing to unsitting off the seat and losing your dynamic compression, and bleeds off either to the intake port or to the exhaust port. Remember, at that point, the intake port still is in a vacuum condition, or if it's port recovered, it will still have more pressure inside the combustion chamber that will go upstream to the intake port, and also the exhaust still dormant at that point in time, or the exhaust cycle, and it will also dynamic compression will bleed off if and when the intake exhaust valve is gyrating. It will bounce off its seat or vibrate off its seat, losing its seal. This said, let's look at this new kid on the block, the Conical. There are distinct advantages that cannot be ignored. First one, when you look at the retainers, this is a retainer made out of titanium. Impressive as it is, this is made out of steel. But guess what? When you feel both of them, that's titanium, but I feel this is still lighter, or just about the same. Remember, in a high RPM engine, valve weight, retainer weight, all that comes into play. Push rod, not so much, but the business end of the rocker arm does have a lot of influence on RPM potential. And so does the retainer. The mere fact that this is narrower towards the end requires a smaller retainer. That by itself is big. Just look at the dimensions. I have to see if they make a titanium version of these that is even more lighter than that would be. But if you compare a steel retainer to this guy here, big difference. Here we have all three retainers here. The titanium, a steel one, kind of worn out, but still good, and the Conical. I wish I had my gram scale. It went poop on me, but I would certainly. It feels like this about 4 times the weight of this one. I would give you guys more information about this later on, but this is really heavy. This one, you could barely tell the difference, but this definitely, the steel one is about, I would say, 4 times more weight-wise. That is significant in a high RPM engine. So there you go, guys. You can see the difference there. Now we're looking at the Conical right here. The bottom diameter progressively gets smaller. When that happens, the Conical's diameter changes the natural frequency of every coil. Right here, once one coil starts to vibrate, since they're all in the same dimension, they will start to gyrate like a team, like a basketball team. They start bouncing all over the place. This one here, they don't play that game. When any part of these starts to gyrate or has harmonic oscillations, it will be isolated to that one spot, and when it goes up towards the other diameters, it tends to cancel out. That is very important. That's why this is more stable at high RPM compared to this old traditional Valvespring. Remember, the decreasing diameter lessens the mass on the whole spring itself, especially right here on the top, which greatly contributes greatly to resonance stability. Remember that. Okay, so that would be one of its biggest advantage. Now, Decreasing coils provides different critical frequencies, reducing the hula hula dance effect. All right, guys, this is very important. When it vibrates right here, it dissipates while it goes to the other diameter changes. Or let's say it starts right here. It won't progress to that because they are different diameters as opposed to here. Once it does that, it goes through the same coils all around. This guy, that's a real teamwork there. Destructive teamwork. This one, hardly any of that. Therefore, this one responds very, very different. Each and every coil is like independent. It does respond differently to increasing lifts. What's compressing or releasing, they're all doing and getting affected differently than the standard spring. There are distinct advantages that cannot be ignored. First one, when you look at the retainers, this is a retainer made out of titanium. Impressive as it is, this is made out of steel. But guess what? When you feel both of them, that's titanium, but I feel this is still lighter or just about the same. Remember, in a high RPM engine, valve weight, retainer weight, all that comes into play. Push rod, not so much, but the business end of the rocker arm does have a lot of influence on RPM potential. And so does the retainer. The mere fact that this is narrower towards the end requires a smaller retainer. That by itself is big. Just look at the dimensions. I have to see if they make a titanium version of these that is even more lighter than that would be. But if you compare a steel retainer to this guy here, big difference. Here we have all three retainers here. The titanium, a steel one, kind of worn out, but still good. And the conical. If I wish I had my gram scale, it went poop on me. But I would consider, it feels like this about 4 times the weight of this one. I would give you guys more information about this later on, but this is really heavy. This one, you could barely tell the difference. But this definitely, the steel one is about, I would say 4 times more weight-wise. That is significant in a high RPM engine. So there you go, guys. You can see the difference there. I see a lot of you make comments about my ways of explaining simple terms or highly technical terms in simple ways that many will understand. Therefore, I will do the same with this valve train video. In essence, frequency of vibration, harmonics, all that oscillation, all these stresses on a valve train, I can explain this way. If you look at the valve train, or the coil spring in particular, like a bridge. When you have a bridge that is spanning across a river, the situation comes in when you have people walking through. I will basically conclude and describe oscillation as, or the absence of oscillation, or dynamic frequencies, or all these stresses on a valve train is like a bridge when there's 1,000 soldiers coming from both sides. When everybody's walking, all at different, some are walking short steps or taking short steps, the other ones are taking larger steps, all at different times. But here's destructive harmonics. If each and every one of those soldiers are in lockstep, all stepping at the same time, boom, 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 from both ends, guess what's going to happen with that bridge? It's going to collapse. Because when everybody's spread out, just like the conical spring, the bigger windings on the bottom to the smaller one, they're all doing different things. But the standard spring, since one oscillation on one coil is the same as the rest of them, it's like a bunch or 1,000 soldiers walking in lockstep, crossing the bridge, all marching, stomping their feet or their boots at the same time, and this bridge is gonna go like this, boom, 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 and collapse. Best I can describe it, guys. Resonance is a bitch. No, I shouldn't say that, bad word. Anyway, resonance is really destructive. And I will also touch bases on frequency of resonance, or I'll also touch bases on frequency of vibration and all this destructive stuff unseen by the naked eye, and we will touch bases with that, and I can also explain those. Thank you very much, guys. Please subscribe, like, and share. I need your help so we can keep this going. Thank you very much. Appreciate all the feedback and the support. Good night.